So in my Pharma Chemistry Academy YouTube channel, this is the third video of stereochemistry topic. So that in this video I am going to discuss about elements of symmetry. It is helpful for identify superimposability of compound on mirror image. To identify the superimposability of a compound on mirror image, it is useful to know the optical activity of a compound. So the compounds which have the elements of symmetry, they are optically inactive. So chiral compounds does not have the elements of symmetry, while achiral molecules have the elements of symmetry. So it is mainly three types. So number one is plane of symmetry, POS. Second one, center of symmetry, COS. Next, third one, axis of symmetry. First we discuss about POS, plane of symmetry. It is an imaginary line of a plane, which divides a molecule into two equal halves. One half of molecule is mirror image of another half of molecule. So when we divide a molecule through the plane, so one half of the molecule is the mirror image of the molecule. So the compounds which have the plane of symmetry, so those are optically inactive compounds. So we can explain the plane of symmetry with an example. So that is tartaric acid. So the IUPAC name of tartaric acid is 2,3 dihydroxy 1,4 dicarboxylic acid. So 2,3 1,4 dicarboxylic acid. So in order to know about the chiral compounds and achiral compounds, watch my second video, chirality and achirality. So come to the example. So we can write the structure. So 4 carbons for tartaric acid. So number 1 and 4 are carboxylic acids, and number 2 and 3 have the hydroxyl groups. So next, satisfy the second and third carbon with hydrogens. So this is the chiral center, because 4 different groups are attached to this one, and this is the chiral center. So in tartaric acid, through this plane, so when I frame a plane through this imaginary line through this plane, so this is part half of the molecule is the mirror image of another half of the molecule. So I framed a plane in the vertical position. So if you write this plane, imaginary plane in in vertical position, so those two will be on mirror images of each other. So the compounds which have the plane of symmetry are having the optical inactivity. So the in plane of symmetry is mostly observed in achiral compounds. So next second one we are going to discuss about is COS, center of symmetry. So it is an imaginary point passes through a molecule. It is the point, center point, passes through a molecule, it is an imaginary point, passes through a molecule. So from that point, if you draw one line, so draw one line, on other side equal line will form. That means the two atoms or two groups in a molecule equal distance from center. So equal distance from center. So for that also we are so the compounds which have the center of symmetry, those are optically inactive compounds. So example for that, we are taking the same example, tartaric acid. So I am writing the structure of tartaric acid. So carbon, so which is having the hydrogen, hydroxyl group, carboxylic acid. At third carbon, I am writing the same structures, COOH and hydroxyl group. So this is the center in a molecule, so which is the center of symmetry point. So through this line, when I draw a line from the center to the carboxylic acid, so then this second on other side of carboxylic acid will be the equal side. Similarly, when I draw a line to hydroxyl group, so in left side direction, equal direction, so the distance between these two will be the same, and distance between two hydroxyl group on opposite sides will be the same. So this is the center of symmetry. So in this line, in all groups in a molecule are intersects at one point. So when you draw two lines from opposite directions. Next another example is the trans 1,3 dimethyl cyclobutane. Trans 1,3 dimethyl cyclobutane. So first I am writing the cyclobutane structure. So butane means 4 carbons, 4 carbon cycloalkane compounds. So at 1 and 3 positions, methyl groups in trans position. So 1, next methyl group in trans position, hydrogen. So 1, 2, 3, 4. Okay, so here the groups will be 2 hydrogens and 2 hydrogens. Here is hydrogen. In this compound, in trans 1,3 dimethyl, so this is the center point. So from this point, so when I draw a one line through this methyl group, so next on the opposite side, equal distance and equal line will be formed. So this is the center of symmetry point. So from hydrogen at 1 and 4 position, so when I draw a line to this hydrogen and opposite direction, equal distance will be produced. So this is the center of symmetry point. So next in this video we are moving forward for third type. So that is axis of symmetry. So third one, sorry, so problem. Third one, axis of symmetry, AOS. So it is an imaginary axis. It is an imaginary axis. When a imaginary axis, through that axis, when we rotate molecule through certain angle, molecule through certain angle through one axis, so that after rotation similar compound will form. So axis of symmetry, when it is an imaginary axis, through that axis when we rotate compound or molecule with some certain angle, will produce the same or original compound. So the compounds which have the axis of symmetry are optically inactive. So for this axis of symmetry we are taking an example, so that is boron trifluoride, BF3. So B boron, F means fluorine. So in this boron trifluoride, so the shape of this boron trifluoride is triagonal. Okay, so center boron. So next F1, F2, F3. So when I rotate the F1 through this perpendicular to the triagonal shape, so when I rotate in 120 degrees, so then what will happen? So this is C31, so that means 3 times rotation of the boron trifluoride will produce the original compound. So 3 times rotation will produce the original compound. So when I rotate the F1 to the perpendicular to the triagonal shape, so in this direction, when I rotate 120 degrees, so so F1 on 90 degrees comes here, so in 90 degrees, so next 30 degrees, so it is F1 comes to F2 place. So where F2 goes here, F3 comes here. So boron, okay, so F3 and F1 and F2. So next on another rotation in 120 degrees direction rotation, so produce boron in the middle only. So here we are moving only fluorines. So F2 comes here, so F3 goes here and F1 will comes here. So next another one more time of rotation of this boron trifluoride will produce boron. So on 90 degrees comes here, so more 30 degrees, so will produce F2 will come in place of F3. So F1, F2 and F3. So this 120 degrees rotation, so will produce a similar compound. So this certain angle may be 120 degrees, 180 degrees, 240 degrees, 360 degrees. So that axis of symmetry, the number of rotations is equal to 360 degrees divided by theta. So with what angle we are rotating the molecule, so that will, by this formula, how many times we have to rotate, we can determine for a molecule. So next another example, water molecule. So it has the with 180 degrees of rotation will produce C2AOS, axis of symmetry, that is 2 times rotation, two time fold rotation. So oxygen, so which having the HA and HB hydrogens. So when I rotate this water molecule 2 times, so with 180 degrees, with 180 degrees rotation, linear rotation, so oxygen, so HA comes here, HB opposite. So next one more time C2 one rotation, so will produce the similar compound HA and HB. Okay, so here C2 is the so 1 is a folds, 1 2 3 folds for boron trifluoride, whereas water is for um, 2 times, one and second time. So right, so C3 indicates the number of times on rotation will produce the original compound. So with this, I hope I have given enough information for the elements of symmetry. So if you like my video, so please share and like and subscribe for more further videos. Thank you.